Hello and welcome to our fourth year design project seminar. We've developed a novel nanomaterial-based device that's a color writing surface. So today we'll be going over our design process with you. First we'll go over the issues that motivated us to develop the device. Then we'll go over the background theory behind the operation of the device. And finally we'll examine our prototype architecture and whether it met our criteria, as well as possible design improvements we could make. All right, so writing has always been an integral part of society, and the technology behind writing has evolved over time. It began with just stone tablets, finally onto papyrus, paper, and now more recently even electronic tablets. There's several issues with the modernly used writing surfaces, however. For example, paper is not very reusable. There's a lot of lumber consumed every year in the production of paper, and also paper mills produce a lot of toxic waste and fumes. Electronic tablets as well also have a very limited battery life. They need frequent charging, and they're relatively expensive. In response to these issues, we wanted to develop a material that would produce a multicolor display, was reusable, and also consumed no electrical power at all. So there's two types of magnetism that are used in our prototype. The first is paramagnetism. Paramagnetism is when the domains of the magnetic material can be aligned by an external field. However, they randomize when an external field is not present and they don't attract each other. Ferromagnetism and ferrimagnetism are two other types of magnetism that when a magnetic field is applied, the domains of the material will align, creating a permanent magnetization that will exert a magnetic field even after the removal of the applied magnetic field. The degree of the alignment will depend on the strength of the applied field, and that will determine the strength of the magnetic field that it exerts after permanent magnetization. Now, in the figure on the right, you can see aluminum, nickel, cobalt bars that we used in our prototype. And so the reason why we chose aluminum, nickel, cobalt is primarily because of its high remanence, which is the maximum magnetic field that it can exert after full magnetization. So when a very large magnetic field is applied to it, this is the maximum magnetic field that remains after removal of the applied field. In addition, it also has a very low coercivity. This is the minimum magnetic field that is necessary in order to change the magnetization of the material. A low coercivity means we don't need very large magnets in order to actually magnetize the material itself. So another important property of ferromagnetic and ferrimagnetic materials is the Curie temperature. This is the temperature above which the materials behave paramagnetically. Now, as the size of ferri and ferromagnetic materials approach the nanoscale, they exhibit a property called superparamagnetism, which is when their Curie temperature goes to around room temperature. Now, these materials still maintain the high magnetic susceptibility of the original bulk material, and this means that when they're aligned by a magnetic field, there's a very strong attractive force exerted between each other. So the second component of our design was iron oxide nanoclusters. These are composed of Fe3O4 core, and there's several particles that form a cluster. And now they're also surrounded by a negatively charged polymer surfactant that creates a negative surface charge on the particle. We measured the particles that we created with zeta potential and found that the zeta potential is around minus 40 millivolts, which is below the necessary minus 30 millivolts in order to prevent aggregation of the particles in solution. So these ferrimagnetic Fe3O4 particles are at the size that they behave superparamagnetically, meaning that under no applied magnetic field, their domains are on average random, and the particles don't exert a magnetic force between each other, and the only force acting on them is the repulsive electrostatic force. However, once a magnetic field is applied, then the domains will align and the particles will attract each other. This will result in the magnetic force between the particles countering the electrostatic force. So as part of these nanoparticles, a very important aspect of them is the size of the actual particles, because this will determine the surface charge as well as the interparticle spacing when a magnetic field is applied. So we measured our particles with dynamic light scattering, and we found that the diameter is approximately 250 nanometers. Now, 250 nanometers is above the ideal 140 nanometers to get the properties that we desire. However, we still see the phenomena enough to get an effective prototype. We also examine them under scanning electron microscopy in order to confirm their morphology and make sure they were the shape and size, or the shape expected. So we can see from this image that they are spherical and they're composed of smaller nanoparticles that form an aggregate cluster. So the electrostatic and magnetic forces, they balance at an equilibrium distance when there's an applied magnetic field. The distance will depend on the magnetic field, as the dipole strength is dependent on the strength of the magnetic field applied. And the particles will then form, with this equilibrium spacing, the particles will form a 3D array known as a photonic crystal. Photonic crystals are a periodic variation in the refractive index of a material. And what happens with these materials is that at each interface, light is reflected, and the light from the reflected rays end up interfering constructively and destructively depending on the optical path differences. Now, by controlling the thickness of the layers, you can get specific wavelengths to interfere constructively and specific wavelengths to interfere destructively. With our nanoparticles, with our material, the nanoparticles form one layer of the photonic crystal, and the other layer is the water solution that they're suspended in. So here you can see the nanoparticle solution that we've created under varying magnetic field strengths. Under a very weak field, you can see that the interparticle spacing is very large, and so this means that a very long wavelength, such as red, is reflected. Under a medium field, green is reflected, and under a very strong field, blue is reflected, though it's kind of hard to see with the glare here.
Our idea with Papyrum Magnetica is to incorporate the phenomena that Kenji just described into one surface which can be used to record what was written on it. Essentially, there are two functional layers. On top, we have the solution layer, which contains our nanoclusters, and this is the layer responsible for providing color to our prototype. Underneath is the hysteresis layer, which is required in order to record what has been written on it. So, upon applying a magnet to the surface, the magnetic field is able to magnetize the hysteresis layer and create a localized magnetized point. In turn, this magnetic field allows photonic crystals to assemble within the solution layer, and those are capable of reflecting back only a single color. Now, once the magnet has been removed, the hysteresis layer maintains the magnetic field within our device, and thus the photonic crystals are maintained in the solution layer, and that reflected color can still be observed even without the magnet that was initially used to write it. Now, erasing is just as simple. All that's required is another magnet that has a weaker strength and the opposite polarization. So upon applying that, it flips some domains within the hysteresis layer so that the net magnetic field is much weaker. As a result, we no longer have photonic crystals in the solution layer that are capable of reflecting within the visible spectrum, and the solution returns to its original color. Of course, we also need a container for our device, and to do that, we elected to use 3D printing. We decided to do this because it is a relatively inexpensive method, yet still allows us to obtain moderately complex shapes. So there are two plates that we have. As you can see in the figure, the top plate is composed of an array of wells, and this is where our nanocluster solution is deposited into each. So this confines the particles into a specific area of the display to essentially act as pixels. In between the top and the bottom plate are the magnetic hysteresis bars, and that is where the information has been stored. Now, to seal our wells, we used a simple overhead projector slide to act as a transparent cover, And to hold it all together, we use simply super glue and black electrical tape to improve the appearance. So if you could get the light. So as you can see in the picture of our prototype, the normal color is a brown. However, upon using a magnet to write with it, we are able to change the color of that into a whole spectrum. However, it's not very accurate. I think here we're trying to draw an N, although if you tilt your head 90 degrees, you could also say it's a Z or a 2. But mainly from this, we were able to demonstrate a proof of concept. However, it was not very accurate in being able to draw stuff, mainly because we needed a large magnetic strength in order to induce, to magnetize the hysteresis layer underneath this prototype. However, I found after 5 years of engineering that sometimes you do get the best results in the work that you start in, the day before something is due. Well, that's exactly what happened with us. This is the second prototype that we just constructed yesterday. Instead of the Alnico bars, we use a ceramic magnet, which is a continuous sheet. So the overall thickness of this prototype is much thinner, and as a result, we need a much weaker magnetic field in order to actually magnetize the hysteresis layer and obtain the photonic crystals we need. So as you can see, we can still obtain multiple colors, and the writing is much more accurate since we can use smaller magnets with weaker magnetic fields. So looking back at our objectives, did we meet them? Well, we were able to obtain a whole spectrum of colors with both prototypes, and we were able to draw accurate designs with our second prototype. However, the downfall is that we can only get a spectrum, and it's very hard to get a single isolated color. This is mainly due to the fact that the magnetized points will still have the magnetic field permeating from it, although it weakens with the distance from that point, and thus there are photonic crystals that can form which still reflect within the visible spectrum on the outer edges of the design of what was written. Now, our prototype can be written and erased for both of them. However, an issue we have is that the images tend to distort over time due to sedimentation. This is a combination of both gravity and due to the fact that there is the magnetic hysteresis layer underneath, which exerts a constant magnetic force on the particles to drag them down. However, we were able to achieve our objective of having no power consumption. All that's required to write and erase are just simple magnets. So from our conclusions, there are several recommendations we can make to improve the design of our prototype. As Kenji mentioned, our nanoclusters were not the desired size. They were significantly larger. In the literature, it was reported that a size of 140 nanometers is optimal to achieve the most vibrant color, as well as being easiest to achieve a very wide spectrum. So if we are able to improve the process into a way to actually match that size, then we should be able to obtain a much better and more vibrant display. Additionally to that, we are also able to investigate other polymers to act as the coating for our nanoclusters, and this could help the issue of sedimentation that we observe. Now, as for the mechanical design of our prototype as well, we could reduce the overall thickness, as we observed in the second prototype. By greatly reducing the thickness, we greatly reduce the magnetic strength that is required in order to obtain visible results on our display, and that is mainly due to the lower strength that is required. Additionally to that, there is a force that can be felt when you use a magnet to write on it, and if we can reduce the magnetic field that is actually required to write, that should be less distracting to the user when they're using our device. Lastly, we can also use smaller solution wells in order to better confine the nanoclusters to specific areas. One of the issues with our second prototype, which did not feature wells, was that the nanoparticles could easily be clustered, could easily be drawn to points that have been magnetized, and thus it will distort the overall image over time due to the fact that the concentration of nanoclusters at that area will be much higher. These are our references. They are available upon request. We thank you for your time, and we'll now be accepting any questions you may have.
So we attempted to make them at first, and the fabrication procedure that we used wasn't successful, and we weren't getting very monodisperse and good properties with our nanoparticles.
You couldn't get particles at all.
Yeah, exactly. So we ended up, actually, we discussed our project with Professor Gu, who does work with iron oxide nanoparticles. And one of his graduate students, Tim Lashuk, he actually ended up synthesizing the size of particles that we requested. And that's what you saw in the actual final prototype. Yeah.
200 nanometers a cluster, right? Do you know how small the particles inside?
We're not
We weren't able to measure that.
Yeah.
So did you measure the magnetization curve of the iron oxide?
No,
That's
we haven't.
very important
Yeah.
to you guys.
Yeah, I suppose that's very important to ensure that they are behaving super paramagnetically and they're not simply ordinary ferrimagnetic iron oxide particles. But yeah, we didn't have an opportunity to measure that.
I assume the magnetization property would be depending on those crystal size within the cluster, but your color would be more dependent on the cluster size, right? So those two parameters potentially can be two.
Yeah, yeah. So definitely the two particles are extremely, the two properties are extremely important. The size of the particles also affects their magnetic properties, and part of the reason that 140 was the ideal size was because when you have the photonic crystal, the ideal sizes to have are 1/4 of the wavelength for each layer, and so because we have a tunable photonic crystal, it's impossible to have it 1/4 of the wavelength for all colors because the particles themselves can't change size. But we wanted to get a particle size that's in between, and I believe that with the refractive index of the particles, green is approximately corresponds to 140 nanometers, and because we got a larger size, our peak wavelength for reflection would be around red instead. And so that's why we're not able to get a very vibrant blue color, and our green is slightly dimmer. If we had green as the central peak, then it would have been more uniform. The red colors would still, the red and the blue would still be slightly less than the central green color, but at least then the red and the blue would both be visible instead of just really the red being visible. You're welcome. Are there any other questions? All right, thank you very much.